Okay, now that we've talked about phase shift and did some examples with it, we're ready to start doing some graphing with phase shift. So here's example one of graphing a sinusoidal function with the phase shift. So remember, sinusoidal is just a fancy term for sine or cosine. So here in example one, we have a cosine. So graph y equals -2 times the cosine of pi over 3x minus pi over 3, and then plus 1. And we're also going to find the domain and range. So basically what we're going to do here is follow a set of steps here that's almost identical to the set of steps that we followed when we had no phase shift. We'll talk about similarities and differences at the end of the video, and we'll make some comparisons and some observations also. So really, a lot of the things that we did without a phase shift, we're really going to do it again here. And we're actually going to see that not a whole lot's different. So step one, find the period t. So remember, t is 2 pi over the absolute value of omega. Okay? So before we move on, we should probably identify what omega is, and maybe some of the other constants too. So remember, in general, it's y equals a times the cosine of omega x minus phi, and then plus b. Okay. So what are our constants here? Well, here a is -2, right? A is -2. A is -2. Omega is the thing being multiplied by the x. It's pi over 3. So omega is pi over 3. And then remember, it's omega x minus phi. So pi over 3x minus pi over 3. So phi is pi over 3. Okay, phi is pi over 3. Because it's omega x minus phi. So omega is pi over 3, x is x, minus sign, and then phi pi over 3. Okay? And then plus b, so b is positive 1. Okay? Now we probably didn't really have to identify all of those constants, but it's not a bad idea too in general, just so you know what you have and can refer to it later if necessary. So let's zoom in a tiny bit maybe. Okay, so then t is 2 pi divided by the absolute value of omega. Omega is pi over 3, it's already positive, so we don't need absolute values. So 2 pi divided by the quantity pi over 3. Okay. Now if you divide by pi over 3, you're really multiplying by 3 over pi, so that's 2 pi times 3 over pi. Pi is canceled, that's great, we have 2 times 3, which is 6. Okay. So that's step 1, find the period t, and it's 6. Okay, step 2, divide this crazy interval into 4 subintervals of equal length. This will make 5x values. So again, just like when we had no phase shift, we're going to take an interval, which is a little bit different here, and then divide it into 4 subintervals. But what's nice is, even though this step sounds really complicated, it's actually not that bad. So what's the deal with this interval here? Well, remember, phi over omega, that is the phase shift. Okay, and then if we take phi over omega and add t to it, remember t is the period. So really what we're doing here is we're taking an interval that starts at the phase shift and ends one complete cycle later. Okay, so we're taking one complete cycle and we're going to get 5x values from that cycle, and then we're going to use those x values in step 3 to get y values, and then that's going to give us 5 points on the graph, and then in step 4 we're going to plot those points. Okay, so that's really what we're doing here. It's the exact same thing we did when we had no phase shift, but we're just using a different interval. Okay, and we'll talk more about that later in the video, but for now let's keep going. So let's figure out what this is and what that is before we move on. So now for step 2, we're going to say we start at phi over omega. Okay, so this interval starts at phi over omega, so let's figure out what it is. So phi over omega, well, phi is pi over 3, and omega is also pi over 3. So phi over omega is pi over 3 divided by pi over 3. Divide something by itself, you just get 1. Okay, so that's nice. Now where do we end? We end at phi over omega plus t. And at phi over omega plus t. Phi over omega, we just found out that's 1. T, we found out earlier, we found out earlier that t is 6. Okay, so phi over omega plus t, that's 1 plus 6, which is 7. Okay, so for our specific problem here, this interval is 1 to 7. So we're going to take that interval, divide it into 4 subintervals of equal length, and then that'll give us 5x values. Now what's nice about this is we don't actually have to think of this in terms of intervals. It's just easier to talk about it that way. It's easier to write down the step in terms of intervals, but when we think about it and do it, we really don't have to do it like that. Think of it as intervals. So what we do is, just like we did with no phase shift, we're going to set out this little number line here. Okay, so here's 1, that's where we start, and here's 7, where we end. Okay. Now what we do is, so we have an interval here, we don't have to think of it as that, but we want to divide it into 4 subintervals. So what we do is divide it in half. First we divide it in half. So if we divide it in half, what number is halfway in between? Well, 1 plus 7 is 8. 8 divided by 2 is 4. Okay? Now we do the same thing with both of these guys, and that'll be it for step 2. So let's divide this one in half. 1 plus 4 is 5. 5 divided by 2 is 5 halves. Okay. Divide this one in half. 4 plus 7 is 11. 11 divided by 2 is 11 halves. Yeah, that's 2.5, and this one is 5.5, but it's best to avoid decimals if we can. I think so anyway. So that's it for step 2. Divide this interval into 4 subintervals. So here's our subintervals, this one, this one, this one, and this one. But it does not matter at all. We don't have to worry about the intervals. We don't have to think of them as intervals. The point is that we have 5 x values now. So here's 1, 2, 3, 4, 5 x values. And now in step 3, we're going to use them to find the corresponding y values. Okay, so again, what's going on here, what we're doing, what we did is first we found the period, and then we got that phase shift for step 2. And then we did phase shift to phase shift plus period to get one complete cycle. Okay, so we took an interval whose length is equal to the period. Okay, so we took one complete cycle of the graph, and then we got 5 x values on that cycle. And then now what we're going to do is get the corresponding y values so that we get 5 points on the graph in one complete cycle. So that's what's going on now. So now what we want to do is find the y value at each of these x values. So let's get that going. All right, so let's maybe get rid of this here so we can have just a little bit more room. So that'll be 6. Okay, set aside some space. And now what we're going to do is just take one x value at a time. Okay, so we have 5 x values here. Take one at a time, put them into the function, simplify and see what we get. So this step, sometimes it's the most tedious. It is probably maybe the longest, unless you spend a while graphing. But once you get to the graphing, it's actually not that bad. But anyway, 1 point at a time. So x equals 1, we'll start there. Okay, so we have y equals -2 times the cosine of pi over 3 times 1 minus pi over 3, and then plus 1, okay? Pi over 3 times 1 is pi over 3. Pi over 3 minus pi over 3 is 0. So this is -2 times the cosine of 0, and then plus 1. A little higher. We have some more room. Cosine of 0, what's that? That's 1, right? So this is -2 times 1, and then plus 1. Okay. -2 times 1 is -2. -2 plus 1 is -1. So what we just found out is that when x is 1, y is -1. Okay, so if you remember our videos without the phase shift when we did this graphing thing, this is all exactly the same, right? The only thing that's a tiny bit different now is this expression is just a little bit more complicated to simplify. But it's not even that, you know, we're just subtraction now, it's not really that bad. So the point here is 1 comma -1. Okay? Now what's the next one? Next one is 5 halves. Ugh. Okay, so x equals 5 halves, what's going on? So that's going to give us y equals -2 times the cosine of pi over 3 times 5 halves, because it's x, pi over 3x minus pi over 3. So pi over 3 times 5 halves minus pi over 3, and then plus 1. Okay, so then pi over 3 times 5 halves minus pi over 3, let's simplify that. That's going to be 5 pi over 6, and then minus pi over 3. So get a common denominator, so this is going to be times 2 over 2. So this is 5 pi over 6 minus 2 pi over 6. Okay, so that's equal to 3 pi over 6, which simplifies to pi over 2. That's wonderful. Okay, that's great. So this is -2 times the cosine of pi over 2. And then plus 1. Okay, so let's get rid of this here. Cosine of pi over 2 is 0, so this is negative 2 times 0 plus 1, which is just 1. That's 2 right there. Not that it matters, we're multiplying by 0. So when x is 5 halves, the corresponding y-coordinate is 1. So this is gives us the point 5 halves, comma 1. Okay. All right, what's next? X equals 4 is next. Okay, when x is 4, we have y equals negative 2 times the cosine of pi over 3 times 4 minus pi over 3 plus 1. Okay, so how does that simplify? That's really not too bad, but just to be thorough with the details, let's write it all down. So pi over 3 times 4 minus pi over 3. So pi over 3 times 4 is 4 pi over 3, and then minus pi over 3. 4 pi over 3 minus 1 pi over 3 is 3 pi over 3. 3's cancel, and we're just left with pi. Okay, so this is negative 2 times the cosine of pi plus 1. Okay, that's great. Cosine of pi is negative 1, so this is negative 2 times negative 1, and then plus 1. Negative 2 times negative 1 is positive 2. Positive 2 plus 1 is 3. Okay. So let's erase this here. And then that just gave us the points 4, comma 3. Okay, when x is 4, y equals blah, 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 3. Okay, 4, comma 3. All right, 2 more to go for this step. So now what's next? 11 halves is next. When x is 11 halves, what's going on? And when x is 11 halves, we have y equals negative 2 times the cosine of pi over 3 times 11 halves minus pi over 3, and then plus 1. So we'll simplify this separately. So pi over 3 times 11 over 2 minus pi over 3. So pi over 3 times 11 over 2, that's 11 pi over 6. So 11 pi over 6 minus pi over 3. Common denominator, just like when we did x equals 5 halves. Common denominator, multiply this by 2 over 2. Because our least common denominator is going to be 6, because this denominator is 6, this one's 3, so I have to multiply this one by 2 over 2 to get 6. So then 11 pi over 6 minus 2 pi over 6 is 9 pi over 6. So 9 is 3 times 3, 6 is 2 times 3, common factor of 3 can be canceled, and we end up with 3 pi over 2. Okay, so then this whole expression in here simplifies to 3 pi over 2, and we get negative 2 times the cosine of 3 pi over 2, and then we have a plus 1. Okay, starting to run out of room a little bit, but I think we'll be okay. So then this equals cosine of 3 pi over 2, what is that? That is 0. So this is negative 2 times 0 plus 1, which is just 1. Okay. So when x is 11 halves, y is 1. So this is the point 11 halves, comma 1. Okay. And then last, x equals 7. Let's go ahead and figure this one out. So when x is 7, what's going on? We have y equals negative 2 times the cosine of pi over 3 times 7 minus pi over 3, and then plus 1. Okay, so what does that equal? Well, pi over 3 times 7 is 7 pi over 3. Okay, so 7 pi over 3 minus pi over 3. So let's, kind of running out of room everywhere. But let's come over here and write this. So pi over 3 times 7 is 7 pi over 3. So we have 7 pi over 3 minus pi over 3. 7 pi over 3 minus pi over 3. That's 6 pi over 3, right? 6 pi over 3 simplifies to 2 pi. Okay, that's great. So this is negative 2 times the cosine of 2 pi plus 1. Okay, cosine of 2 pi is 1, so that's negative 2 times 1 plus 1. Negative 2 times 1 is negative 2. Add 1, you get negative 1. Okay? So in other words, what we just found out was that when x is 7, y is -1. Okay, so that's going to give us the point 7, comma, -1. All right, so that's it for step 3. We found all the y values and got the points that gave us on the graph. So now step 4 is plot the points and smoothly connect, extend the graph as needed. So extend the graph as needed just means, you know, all we have here is one complete cycle. So maybe we want to graph 2 or 3 cycles, but anyway, we'll worry about that on the graph. Before we move on though, I want to point some things out. So first of all, if you saw the other videos where we did this thing without the phase shift, you might remember that this nice pattern showed up. When we plugged in the first number, simplify inside the trig function, you get 0 in there. Plug in the second x value, simplify, you get pi over 2 in there. Third x value, simplify, you get pi. Fourth x value, simplify, you get 3 pi over 2. Fifth x value, simplify, you get 2 pi. Okay? Do those numbers sound familiar? 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, those are some of the nicer angles on the unit circle. You know, 0, pi over 2, that's 90 degrees, pi, that's 180 degrees, 3 pi over 2 radians, 270 degrees, and then 2 pi radians, full 360 degrees. So these are the nice numbers on the unit circle. And what's nice is when we did the steps without the phase shift, so these are the steps without a phase shift, these are the steps with the phase shift, they're completely identical, right? The only difference is the interval that we use, and we'll talk more about that at the end of the video. But when we did this without a phase shift, use this interval, we got this nice pattern showing up. Well, the exact same thing will happen if we use this interval here with the phase shift. Okay, so as long as you stick to this interval here with the phase shift, then you'll get this nice pattern showing up here. Okay? And again, we'll talk more about that at the end of the video. But for now, let's move on. So, step 4 now, plot the points and smoothly connect, extend the graph as needed. All right, let's bust out some graph paper here. So, if you want to follow along with some graph paper, if you don't have any, check the video description. There'll be a link in there. You can click the link, open up some graph paper and print it out and follow along with that if you'd like. All right, anyway, let's see. Let's maybe set up a y-axis here. And then an x-axis we'll put here. Okay, so here's x-axis, here's our y-axis. All right, now we're gonna have to set up a scale before we move on. So let's look at what kind of numbers we have. 1, -1, 5 halves, 1, 4, 3, 11 halves, 1, 7, -1. So let's just look at the x-coordinates. That's 1, 2.5, 4, 5.5, and 7. So what I want to do is make each of these grid boxes 1/2 of a unit. So that way it'll be easier to plot the points like 5 halves, where x is 5 halves and where x is 11 halves. It'll be easier to plot those points because they'll fall on the corner of a grid box, as long as we set up our y-scale in a nice way also. So anyway, for the x, this is going to be 1, here's 2, 3, 4, 5, 6, 7. You know, again, what's really nice is we can really set up our scale to be anything we want. Now, if you're given a scale, hopefully it'll be a nice one for the problem and you won't have to worry about any of this. But if you're not given a scale, it's best to set it up depending on what kind of coordinates that you have. Okay, so 8, 9, 10, and 11. Probably don't really have to go that far. Now let's continue this way. So still the x-axis of the same scale, -1, -2, -3, -4, -5, -6, and -7, and, oh, why not, one more, -8. All right. Okay, so that's the x-axis. Now for the y-axis, if we can give it the same scale, that would be good. Let's see if we can. What are the, zoom out a little bit. What kind of y-coordinates do we have? -1, +1, +3, +1, and -1. Okay, so those aren't really too bad. They're not too big, not too small, anything like that. So let's go ahead and give the y-axis the same scale. Okay, now actually for the y-axis, we can make each box one full unit, not a half unit, but it'll make our graph look kind of goofy, and since we can avoid it, let's go ahead and avoid that. So we'll just give the y-axis the same scale as the x-axis. So that's 1, 2, 3, 4. Okay, the largest y value we had was 3, so we don't really have to go beyond that. And then -1, -2, and the smallest y value we had was -1, so we don't really have to go beyond -2. Okay. All right, so let's label that a little better. So that's -2, -1 up there. Okay, so anyway, that's our scale now. Now let's plot some points. Okay, so 1, -1. Let's plot that point. 1, -1. So that's going to be this point right about here. 1, -1. Okay. What's next? 5/2, 1. So that's 2.5, 1. So that's going to be here 2.5, 1, right about here. Okay, so we see that's why I set up the scale the way I did, because now 2.5, 1 is easier to graph. Okay, so that's going to be 5/2, 1. Okay, what's next? 4, 3. 4, 3. Okay, and what's next? 11/2, 1, which is 5.5, 1. So that's 5.5, 1. That's right here. Okay. So again, another 0.5. So that's still in the corner of the grid box because of how we set up our scale. So this is 11/2, 1. Okay, and then 7, -1. Okay, my next is 7, y is -1. 7, -1, that's right about here. Something else I want to point out, when we went through these steps here to get these y values, we didn't actually have to do this step with x equals 7, and the reason is that we already know what y is when x is 1, and we know the period is 6. So if we're at x equals 1, if we go 6 units to the right, we're going to be at x equals 7, okay? And because the period is 6, then we're going to have the same y value. Okay, so remember the period tells you if you go that distance to the right or to the left, you're going to have the same y value. So since the period is 6, I start at x equals 1, I go 6 units to the right, I have the same y value. And we see that it's true. 1, -1, 7, -1. Okay, so we didn't have to go through all this work here actually, but I did want to go through it to point out this pattern that shows up that we'll talk about again at the end of the video. But anyway, let's continue with this. So now, step 4, plot the points and smoothly connect, extend the graph as needed. So now we want to smoothly connect. So we want to be careful here because it looks like we can just connect like a straight line, but we really don't want to do that because it's a cosine graph, right? Remember, cosine has kind of that wavy thing going on. Okay, so let's go ahead and plot it cosine style. So curviness going through here, curviness up through here. Not sure why I'm using a pen, but a little easier to see, I guess. Anyway, continuing curviness here, here. This is actually pretty bad. Okay, so we don't really know where the x-intercepts are, so we don't really have to worry about those. Not terribly good sketch. But anyway, so now this is one complete cycle, right? So we just smoothly connected these cosine style to get one complete cycle. Now what's nice about that is we know, let's zoom out a tiny bit here. So remember also in step 4, plot the points, smoothly connect, extend the graph as needed. We should extend a little bit because we don't have a whole lot going on here. So let's maybe extend and get one more complete cycle. So this is one complete cycle. If we extend to the right, we're going to have that same exact shape over here. We don't really have enough room to extend to the right. So 7, if since the period is 6, then if we go 6 units to the right, 7 is going to be that's going to move over to 13. We don't really have enough room for that. So let's go 6 units to the left. Okay, so remember, the periodic properties tell us that if you move, in this case the period is 6, so if we go 6 units to the right or to the left, then we'll have that same shape, okay? And not just 6, but any multiple of 6. So if I go 6 units to the right, another 6 units to the right, another 6, it's going to be the same thing. So I can go 6 units to the right or to the left, 12 units to the right or to the left, 18 units to the right or to the left, 60 units to the right or to the left. I'm going to have this same shape here, okay? So we do have enough room to the left, so let's go ahead and do that. So all we have to do now is think, okay, where do these points move to if we go 6 units to the left? Okay, well, 1, -1 if we go 6 to the left, all the y values will stay the same, right? But the x values will change. So 1 minus 6 is negative 5, right? So this one's going to go 6 units to the left, so 1 minus 6 is negative 5, so it's 1, 2, 3, 4, 5, 6. Right here, we confirm at negative 5. So negative 5 comma negative 1. Okay. How about this one? 5 halves comma 1. So that's really 2.5. Okay, so 2.5 minus 6 is going to give us negative 3.5, okay, which is right here, negative 3.5 comma 1. Okay, so, and if you're not sure with that, you can just think, okay, let's go 6 units to the left. So start here, 1 units, 2 units, 3 units, 4 units, 5 units, 6 units. So remember, the way I set up the scale, 2 grid boxes is 1 full unit. Okay, so then this is negative 7 halves, comma 1. Okay. And then 4 comma 3 goes to negative 2 comma 3, because 4 minus 6 is negative 2. And again, 1, 2, 3, 4, 5, 6 units. And then 11 halves comma 1, that's 5.5 comma 1. 5.5 minus 6 gives us negative 1 half comma 1. So that's negative 1 half comma 1. Getting kind of cramped in there. And then lastly, not really even a thing, 7 comma negative 1 goes to 1 comma negative 1, which is already there. Okay, so now we just smoothly connect, just like before. So let's smoothly connect. And it's going to have really that exact same shape, but if you're bad at sketching like I am, then it might look a little bit different, but it's, you know, it's just really a sketch. We don't have to worry about it too much. Ugh. Oh man, that is just awful. Okay, so anyway, continuing with that, that could have been a lot worse, I guess, but a little better also. Anyway, so that's really it for the graph. So this is also going to extend. We shouldn't leave it like that. We should extend a little bit this way and put some arrows on it. Okay, arrow over here, and then extend this one a little bit this way. Put some arrows on it. So again, it looks like I went right through 8, but we don't really know what the x-intercept is. There are some things we could do to figure it out. We haven't really talked about them yet. But again, we just don't want to worry about it. Okay, we went through enough steps to get the general shape and location. That's all that really matters. If you want the x-intercept, that's kind of a different thing. Alrighty, so that's it for the shape here, and that's pretty much it for the graph. Now, we also had to find the domain and range, right? Find the domain and range. So what's the domain? Remember, the domain in general, it's the set of all the x values for which the function is defined. What is our function here? Our function we were given is y equals negative 2 times the cosine of pi over 3 x minus pi over 3 plus 1. Okay, that was the function that we were given. Okay. Now remember, you can take the cosine of any number you want. This negative 2 does not affect that at all. This pi over 3 changes nothing. This pi over 3 changes nothing. This plus 1 changes nothing for the domain. Okay, so really, the domain is still all real numbers. Okay, because you can take the cosine of anything you want. You can multiply pi over 3 by anything you want. You could subtract pi over 3 from anything you want. Okay. Then once you've taken the cosine, you can multiply by negative 2 if you want. You can add plus 1 if you want. Okay, so there are absolutely no restrictions on the domain there. Okay, so that's great. In general, if you have a sine or a cosine and all you do is shift it, stretch it, flip it around, whatever, if you're not doing anything too crazy like tossing in a square root or whatever, then your domain is still going to be all real numbers. So that's great. How about the range? A little more complicated, but actually since we have the graph, it's not bad. For the range, what's the small, so remember the range is the set of all the output values or all the y values that appear on the graph. Okay, it's the set of all the y values that the function actually obtains. So what's the smallest y value that this function gets? It's negative 1. Okay, the smallest y value is negative 1, and it happens here, here, and also happens here, and infinitely many other places. But the point is it happens, okay? So negative 1, put a square bracket, oops, negative 1, and then put a square bracket because the function actually does get that value, so we do put a square bracket, okay? And then always put a round parentheses on infinities here. Negative infinity and positive infinity, always get round parentheses. Always, always, always. Here, negative 1 gets a square bracket because it's part of the range, okay? Comma, what's the largest y value? Largest y value is 3. It happens here, infinitely many other places, but the point is it happens. So it's negative 1 comma 3, okay? Also square bracket on the 3 because we actually do get the value 3. Okay, it happens when x is negative 2 or when x is 4 and so on. And also notice that we do get everything in between. Okay, we get everything in between there. So that's why the range is this, from negative 1 to 3 with square brackets and everything in between. Okay, so that's it for the domain and range. Now that's really it for this problem, but there are some things I want to point out, some similarities here. These are the steps that, let's zoom out a little bit. These are the steps that we use for this problem here with the phase shift. These are the steps that we used earlier with the other problems like this without a phase shift. Let's see what's the same and what's different. Step 1, find the period t, exactly the same. Let's skip step 2. Step 3, find the y value at each of these x values, exactly the same. Step 4, plot the points and smoothly connect, extend the graph as needed. That's exactly the same. Okay, steps 1, 3, and 4 are literally identical, whether we have a phase shift or no phase shift, it's identical. Step 2, what's different? Divide interval into 4 subintervals of equal length, and then this will make 5 x values. So what we actually see is that these steps, whether we have a phase shift or no phase shift, they're exactly the same. The only thing that's different is this interval here. But actually, even the interval is the same, because if you have no phase shift, that means phi is 0, which means phi over omega is 0, which means this becomes 0, comma 0 plus t. Well, 0 plus t is just t, so this becomes 0 to t. Okay, 0 to t. If you have no phase shift, this is 0 to t. So actually this, with no phase shift, is just a special case of this with a phase shift. Okay, so zoom out a little bit more maybe. So also remember when we had this special pattern showing up here, if you do this without a phase shift and you use this interval here 0 to t, you'll get this special pattern showing up with 0, pi over 2, pi, 3 pi over 2, and 2 pi. If you do have a phase shift and you use this interval, you'll get that same pattern showing up, which is nice. Now the reason I point that out is because actually, if you have a phase shift, you don't have to use this interval. You could actually still use 0 to t, okay? And actually, more generally, you could use any interval you want as long as it has length equal to the period, okay? So for both of these actually, you don't have to use 0 to t here. You could start anywhere you want as long as you end t units later, okay? Just like here, you can start anywhere you want as long as you end t units later. Now, that's only true in theory. In theory, you can start wherever you want, but if you don't pick a good starting point, then you might be stuck when you have to evaluate the trig functions here, okay? But what's nice is, as long as you stick to this interval here, phi over omega to phi over omega plus t, which reduces to this with no phase shift, as long as you stick to this interval, then you'll always have this pattern show up, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And these really are, I think, the nicest values that you can have. Cosine of 0, cosine of pi over 2, cosine of pi, cosine of 3 pi over 2, cosine of 2 pi. I think that out of all the possibilities, those are the easiest to evaluate, okay? So if you were so inclined, you could just, you could actually follow this exact same set of steps with 0 to t with a phase shift, because it's still valid, right? Because you're starting at some value and then you end t units later. But that's going to change your x values that you get here. And if your x values change, that's going to change how you evaluate here. So what if we use this interval 0 to t? Okay, then we would have started at x equals 0. We would have had x equals 0 here, and we'd have pi over 3 times 0 minus pi over 3, and we'd have negative 2 cosine of negative pi over 3. Okay, it's doable, but it's uglier numbers. Okay, here, since we follow these steps here, we maybe have slightly goofier x values, but even those aren't really that bad. And then they gave us nice y values, okay? So that simplified nicely, and we got 1 comma negative 1. But if we did, if we just used 0 to t instead, which we totally could have, we would have ended up with more complicated expressions here. So the point I want to make is you can use any interval you want as long as it has length equal to the period. Okay, so start anywhere you want, end t units later. But if you follow these steps here, and remember this is really the same as this is just a special case, because this interval becomes this when there's no phase shift. As long as you follow this set of steps here and use this interval here, you'll always get this special pattern showing up, okay? And again, if you really wanted to, you could always use 0 to t, because getting this interval is a little extra work, But if you do have a phase shift and you use this interval, then what's going to happen is you'll have uglier expressions to evaluate here, especially if you have a goofy phi. This wasn't too bad, but I think personally, if you use 0 to t, the more complicated expressions are going to be worse than the extra amount of work in just figuring this out. Okay? So if you just take the little bit of extra work to figure this out, you'll save yourself a lot of trouble that you would otherwise have if you did this with the phase shift. Okay, so really in general, just follow this one here, because this one with the phase shift, it automatically happens to be this one without a phase shift. So really you don't have two sets of steps to remember, you only have one set of steps to remember, because this one becomes this when there's no phase shift. Okay? So that's the point I want to make. So really it is just one thing to remember. And again, just a side note, just FYI, you can use any interval you want as long as it has length equal to the period. But again, I think this is the best interval to use, because if you use this interval, you'll have 0, pi over 2, pi, 3 pi over 2, and 2 pi when you simplify. Okay? And if you use this interval and you don't get these values, that means something went wrong somewhere. So be careful with that. So it's also a nice way to check yourself. Okay? So that's just some things I wanted to point out there. And that's it for example 1. Example 2 coming up in the next video, and we'll see that even though it's going to be a sine function, there's really almost nothing different. The only thing that's different is going to be the evaluations here, but all the rest is exactly the same. And in that video, since we talked about the comparison here, the similarities and differences here, we won't do it again. So the next video will be a little bit quicker. Anyway, that's it for example 1. Example 2 coming up next.